Everybody started out with it going on.
I'll kind of like, you know.
You're good whenever.
Okay, can you guys hear me in the back? In the back, welcome to the AOS sauna. It's super hot, hopefully you can stay awake. I'm super excited to introduce Ed Nowottnick, visiting us from NASA Goddard. A little bit about Ed. He did his BS, MS, and PhD at College Park at University of Maryland, getting his PhD in 2011. After which he did a postdoc at NASA Goddard, which led into this really amazing, productive career so far, where he is currently a research physical scientist. Ed specializes in aerosol research, particularly a lot of advancements in dust and smoke, and you'll hear about a lot of that today, including Earth system modeling, as well as remote sensing approaches with an expertise in LiDAR. Through that, he's been involved in a lot of field work. Some highlights were HS3, which was a tropical cyclone project, and more recently the CPEC-CV, which Ed says is what he's most proud of in his career, and you'll be hearing about today. And a little fun fact about Ed, he's trying to see a baseball game at every stadium around the US and has done pretty well so far. So we wish you well in getting all of those as you go. So I'll turn it over to Ed. Thanks.
All right, thank you, Angela. How am I doing in the back? Can you hear me okay? We're good? All right, so today I'm going to be talking about some of the dust research that I've been involved with. Like Angela told me that this seminar is primarily attended by graduate students, so I kind of included a nice history, I hope, of how we started to observe dust on Earth and get to where we are today. So start things off, question for the audience. Who do you think was the first person to publish on observing Saharan dust on Earth?
Sparrow?
Bueller?
Vasco da Gama.
Vasco da Gama? Any other guesses?
Benjamin Franklin.
Benjamin Franklin? It was Charles Darwin, actually.
Oh,
on the
sure.
beach. So he was on a cruise outside of Cabo Verde. You can read this work at your leisure, but 1846, and I just find it fascinating. You know, the atmosphere was often hazy. Very fine dust was almost constantly falling. They had several astronomical instruments on board, and they were damaged under the exposure of these dust events. And finally, I may remark that the circumstances of dust quantities, of dust being periodically blown year after year over such an immense area. And so this is an image from one of the current satellites. But it's really remarkable that this observation of Saharan dust goes all the way back to the 1800s. And here we are today. 2024 is still a very relevant topic, especially this year. There were numerous reports and theories about how Saharan dust was delaying the onset of our peak hurricane season, which was forecasted to be very active this year. I just grabbed a few headlines from this summer. So, 2024, we're still talking about how dust interacts with the atmosphere. So we've come a long way since the 1800s. Kind of wanted to give a high-level overview of our current understanding. Here's a schematic of Saharan dust being emitted from the African continent. It's lofted in the atmosphere where it can mix and interact with clouds, and it can reach distances as far as the Caribbean, impacting air quality near the surface. So Saharan dust is the largest source of dust aerosols on Earth. These events are emitted at the ground by surface wind processes. So it's a process called saltation, where these sand particles will bounce and the smaller dust particles will be lofted up in the atmosphere, where they can be transported these great distances by the trade winds in the African easterly jet. It takes about a week for dust to get from the source region to the Caribbean, and there have been numerous studies over the years trying to understand how dust interacts with the Earth system. It directly interacts with Earth's radiation budget by scattering and absorbing light. We've seen modifications to both water and ice clouds. And then, as I mentioned, it can travel great distances to impact air quality. Several of you may remember the big dust event in June of 2020. They called it Dustzilla, impacting dust all the way into Texas. What else do we know? So we know that Saharan dust activity peaks during the northern hemisphere summer. We get intense heating over the North African continent, cool waters from the Gulf of Guinea undercut this region and helps to loft dust, where it can be transported by the African easterly jet. It's often associated with African easterly waves, which typically have a periodicity of 3 to 5 days. So I'm pointing at March here. So this is July, peak season. You can see its pathway across the Atlantic. The dust tends to follow the ITCZ. So come March, you can see that plume is transported a little bit further to the south, kind of centered around Barbados in this case. Compared to other aerosol types, dust is typically non-spherical and it's dominated by the coarse mode. So these are larger particles than your soot and your smokes. And so they have a large mass component to the particle size distribution. And we've seen observational evidence that this particle size distribution that carries these large particles is preserved all the way from the source region to the Caribbean, defying classical gravitational settling theory for aerosol particles. As you can imagine, there's a lot of interest in dust impacts on tropical cyclogenesis. We've seen observational evidence that environmental conditions can inhibit development of tropical cyclones. We've also seen mesoscale processes where dust can act as ice nuclei and invigorate convection. This is actually a case I'll show later, but this was sampled by us during a CPEX TV in 2022. And you can see this dust wrapping around the southern flank into Hurricane Nadine. And as I mentioned, dust has many roles in the Earth system. It's known to serve as an important nutrient for both aquatic and terrestrial ecosystems. So dust is primarily has an iron component that is processed chemically during transport into a soluble form. So when it's deposited in the Caribbean, for example, it serves as an important nutrient for phytoplankton. That's kind of a high-level overview of what we do know. What don't we know? And so I've kind of laid these out as a variety of questions, with potentially proposal ideas for you. I don't know, but so we still don't know how source processes in northern Africa impact downwind transport. We don't know how to properly characterize dust shape and optical properties for radiant forcing calculations. This is really important for how we treat these shapes and optical properties in our global models. I mentioned the giant-sized particles surviving transport all the way to the Caribbean. We don't know what processes are responsible for dust getting transported down in the marine boundary layer. What are the associated timescales of that? We've sampled a lot of dust using suborbital assets in the East Tropical Atlantic as well as the Caribbean, but the middle part of the tropical Atlantic has been vastly undersampled. And then what are the conditions necessary for timing dust impacts on tropical storm development? And here I've kind of illustrated some of these things here where we have the NASA GEOS model on the dashed line, 2 different seasons, and these are dust vertical distributions as observed by the CATS LiDAR. And you can see particularly in this Eastern Caribbean case that the model really mischaracterizes the vertical distribution compared to what was observed by CATS. This is a figure from a recent paper that really provides a nice survey of how dust is treated in our models. And you can see all these various models. This is the particle size distribution, the number of size bins. You can see they're all over the place. And so in a model, you have to make a decision. And so it's an open question. How do we represent these processes and improve them in our global models? Okay, so I'm going to go back and give a little bit of a history here. So we talked about Darwin. 1960s, this was really sort of the beginning of Saharan dust transport analysis. And a lot of this was done from Barbados. And one of the first people to really explore this was Delaney, 1967. They had a observational tower out of Barbados. And at the time, this was the space boom, and they were really interested in cosmic dust being deposited on Earth. And so they were comparing and contrasting magnetic and non-magnetic dust distributions. And what they found is these things were lined up perfectly with one another, suggesting that it was terrestrial origin. So that was one of the first findings to really identify the dust was coming from a different region in this relatively pristine area. In 1968, operations were turned over to Joe Prospero, and he operated this surface site well into the 2000s. And he started to build a great climatology of dust surface mass concentrations shown here. This is from his 1968 paper. Here you can really see the seasonality of dust arriving into the Caribbean. And as I mentioned, this site's still operational today. It's now managed by Cassie Gaston. The Navy had a campaign that coordinated with this site called Magpie the last 2 summers, so it's still very relevant for current dust research. Moving into the 70s, the interest started to work its way east. We were starting to try to understand the processes and mechanisms for how dust was getting into the Caribbean. So in 1968, a DC-8 was flown from Barbados to Dakar and back as part of the BOMEX experiment. And these 2 papers here really tried to tie what they saw in the dust particles and timing to synoptic conditions. And so here are the 2 flights. Here's the flight to Dakar. Here's the flight returning from Dakar. Same here. And what you can see is as you move east, they're noting the haze, which was the dust. Similar on the flight out there. And they were using radon 222 to mark as a signature for dust. And these are the curves shown here. And you see they correlate very nicely with these hazy schematics here. The other key thing that they noticed during these flights was the relative position of African easterly wave axes, these arrows here, relative to the peak concentrations of dust. And so what they noted was these large dust events often trailed the passage of African easterly waves. This would come out in their wake. So they started to develop one of the first conceptual models. At the time, there was some satellite visible imagery from ATS-3. And here's one of the first conceptual models that was developed on how dust interacts with African easterly waves. In conjunction with that, they had in situ sampling on some aircraft in that region. And here, these are different seasons. This is winter, it's fall, winter, spring, summer, and these are some of the earliest measurements of the vertical distribution of dust. They had a good understanding of the timing of these events, but what's the vertical distribution? And we can see it, sort of elevated in these high layers as it's transported to the Caribbean. So in the 80s, early 90s, a lot of the research focus was on the emission process. So moving further east, we're using satellite imagery to try to identify potential source regions. What are the regions that we think are favorable for storing these dust particles and subsequently emitted? And at the same time, a lot of laboratory measurements were going on in wind tunnels. And so here's one of the first studies to look at the surface friction velocity and the flux of aerosol necessary to initiate that saltation process. And so this is really critical for developing the thresholds that are used later and still are used in our global models to emit dust by surface winds. So while all this was going on, the Prospero site was going on, the record was long enough where you could really start to potentially unravel ENSO implications on Saharan dust transport and other large-scale climatic forces. I want to call out this paper that Joe wrote in 2021. It is a fantastic overview of this. It goes in much more detail. So if this is of interest to you, I suggest taking a look when you have a moment. All right, so moving on to the 90s. In 1994, NASA launched what was called the LIGHT experiment. So it was a elastic backscatter LiDAR that actually flew on the Space Shuttle Discovery. This is the Space Shuttle flipped upside down, shooting, it's not actively shooting here, but transmitting a laser towards the Earth. It operated for 53 days, and these were some of the first orbital observations of Saharan dust from space. And here we can start to see some of the classic imagery that we see from Calypso nowadays and other LiDAR systems, but really critical for providing the vertical context for these events in relation to the marine boundary layer, clouds, and things of that nature. At the time, it was used to sort of validate the conceptual model by Carey and Pudi in 1999 for the case studies that they were analyzing. In the 90s and 2000s, this is when dust modeling really took off, and this was really enabled by some of the satellites that were launched at the time. So we had NOAA's AVHRR, the NASA TOMS instrument, which provided measurements of aerosol absorption. And that was really critical to map dust source regions, because dust is an absorbing aerosol. It's sort of the first crack at saying, hey, these are the more preferential reasons for emitting dust to be transported downwind. At the same time, computational resources really evolved to go from simple box models to full dimensional modeling where aerosols were fully coupled to the atmosphere. So the full process was simulated, the emission process using these wind tunnel experiments, coupled with the dynamics of the atmosphere, and then convective and removal processes were included as well to remove the aerosol particles downwind. So now we're getting into kind of the heyday of the EOS era, and this really advanced our understanding of dust transport. We had the NASA A-Train, which started to be launched in the early 2000s. You can see this suite of instruments. I'm sure you're familiar with most of them. Were meant to probe the EM spectrum to look at trace gases, clouds, precipitation, and were really critical for performing radiation calculations, particularly for aerosols. This allowed for the quantification of dust events, optical properties, their seasonality, and were fundamental for developing aerosol assimilation techniques. So similar to your weather forecast models where you have observations of temperature and pressure to constrain your model, efforts were made to assimilate passive observations of optical thickness to constrain the aerosol state in the modeling and hopefully improve the forecast. This enabled studies, this is Kaufman et al., to estimate the amount of fluxes of dust that came off the coast and were deposited in the Caribbean. And so these really provided key sort of mapping of dust events that were key for understanding their impacts, particularly radiatively on the Earth system. Coincident with that was the development of the aerosol robotic network of sun photometers. This is their current map as it stands today. These were developed to validate, to a large degree, the modus retrievals of optical depth, but have also been critical for providing high spatiotemporal coverage of Saharan dust events. So we have point measurements that are really important for filling in the temporal gaps from the A-train that passed by twice per day. One of the key missions from the A-train was the Calypso mission. And similar to light, the Calypso mission provided the 3D measurements of clouds and aerosols. And so that launched in 2006 in the same orbit as Modus Aqua. And it was really powerful for tracking dust events as they marched their way across the tropical North Atlantic. It really helped to validate aerosol transport and removal processes in the global models. An example of this is from one of my papers where I took the Calypso aerosol typing. The dust is the yellow and oranges in each of these panels. And here I'm comparing it to Mera Aero, which is the precursor to Mera 2. And it's really fundamental for identifying transport and wet removal biases in the model. So from my point of view, the things that really advanced our understanding of dust and transport processes were the field campaigns that I'm going to go over next. The first of which I want to talk about was the Puerto Rico dust experiment. And so this was an in situ payload based out of Roosevelt Roads, Puerto Rico. And they were there in July 2000, so a long time ago. But this uncovered two really critical, or provided two critical papers that contradicted our conceptual model developed by Carey and Cootie. First of which was Reed et al., which showing that these large particles were transported all the way and maintained vertically and in terms of their particle size into the Caribbean from the source region. And then the other one is Maring et al. And he contrasting aeronet observations of dust from Azania, the Canary Islands, to Puerto Rico. And he noted again, confirming this, that these large particles were maintained all the way into the Caribbean. Another relevant mission was the TC4 mission. This was in 2007. This was primarily a tropical convection mission. Dust was kind of a secondary component to this mission, but there were a few nice case studies that observed dust. You can take a look at the payload here. This is the heyday of NASA airborne scientists. I don't know how they afforded this, but we had the WB-57, tons of cloud probes, the NASA DC-8 with dropsondes, radiation measurements, particle size measurements of aerosols. And then we have the ER-2, which is an old U-2 spy plane equipped with a remote sensing payload. And so one of the things we saw in the TC4 data, so this is the coast of Costa Rica here, we saw the Saharan dust here, and we would often see the concentration of dust and the backscatter diminish quickly as it hit the coast. We can also see it in the MODIS data. You can see it along the coastline here, the optical depth decreased from about 0.3 or so to 0.1 as soon as it hit Central America. And at the time, the state-of-the-art GS5 model, you can see that that dust event was being transported well into the Pacific. And so what this enabled us to do is really revisit some of the wet removal processes. This is a very convective region. It allowed us to improve our parameterization of dust removal in this region to match what we're observing from both MODIS as well as the LiDAR data in this case. We had NAMA in 2006. This was a pretty comprehensive mission as well. In the back, I apologize, you may not be able to read this, but lots of remote sensing, instrumentation, in situ measurements of aerosols. We had a LiDAR on board called LASE. And while there were 6 cases that they flew where dust was in the vicinity of African easterly waves, that was sort of the main objective of this mission. The environmental conditions suggested that dust was, in fact, an environmental inhibitor of tropical cyclone development. However, as I mentioned earlier, more on the mesoscale processes, they saw several examples of dust invigorating convection. And so here's a combination of APR-2, I believe, airborne radar, or I'm sorry, I think this was Jerry's radar. But here we have reflectivity here, and then dust observed by the LASE LiDAR here. There's evidence for enhanced convection. Hypothesized that dust was acting as an ice nuclei in these cases. So again, sort of conflicting thoughts on the role of dust on tropical cyclogenesis. Angela mentioned HS3. This was my first field campaign that I participated in as a forecaster. This one was, the conception of this was pretty neat. We had 2 Global Hawks at the time, primarily a remote sensing payload, LiDAR, we were scanning his from here, dropsondes, various frequency radars. And the goal here was to look at one of the goals was to look at how the Saharan air layer impacted the development of tropical systems. And so, unfortunately, we only had a handful of cases where we had dust in the vicinity of developing systems, one of which was Hurricane Nadine, which turned out to be the and still is the fourth longest lived hurricane in the Atlantic. And while the hurricane persisted for many, many days, some modeling analysis that I did in 2018 showed that we best matched the observed pressure and track when we included both dust radiative processes and as well as allowed dust to serve as an ice nuclei in our simulations. So that was an interesting finding from this case in particular. And I wanted to pay acknowledgement to some of the great dust field campaigns done by some of our European colleagues. There were two called SANUM 1 and 2. These were primarily focused on understanding dust optical properties, particle size distributions, more on the microphysical side. But then they had Sol Trace in 2013, and this was a pretty neat case study, or a campaign, excuse me, where they're actually able to perform a Lagrangian, semi-Lagrangian tracking of a dust event across the Atlantic. And they also had shipboard measurements as well to characterize the passage of dust events over a week's span in the Atlantic. And this is kind of funny, there's this conceptual model that's published in this paper, and you look back at what was in the Prospero paper, and it's really not all that different. So it's, more things change, the more they stay the same, I think. Okay, so moving on to the CPEX CV campaign. This is a campaign that Angela and I were a part of in 2022. We also had key contributions from Ben Rodenkirch, as well as the Geo Worldview team for supplying us near real-time satellite imagery. We have an overview paper that's an early online release with BAMS, so take a look if you're interested in this. So a little bit of history about CPEX CV. So this originally was conceived to take place July of 2020 out of Cabo Verde. We're in the middle of a pandemic, so we had to postpone it here. In 2021, operations outside of U.S. territory was still a challenge, so decided to deploy in St. Croix, U.S. Virgin Islands. And so we conducted 7 research flights in late August, early September of 2021, captured primarily tropical cyclones and tropical storms as part of this campaign. We also did lots of validation of ESA's spaceborne wind LiDAR aerosols. You can see some of the long legs there associated with that validation. We had a wind LiDAR on the DC-8 for this as well. This campaign, unfortunately, was tragically cut short due to the passing of Gail Skowronek-Jackson, a program manager for the Weather and Dynamics program at NASA headquarters. And so it was resumed in 2022 in September, out of Cabo Verde, where the campaign was originally intended. And so we had 4 science objectives for CPEX CV, the first of which was really focused on large-scale environmental impacts between African oceanic waves, the ITCZ, convection. The second of which was more focused on marine boundary layer processes, in particular cold pools. We were chasing a few of those during the campaign. On the dust side, we were still looking for mechanisms to support the long-range transport of dust. So we're trying to identify shear zones, convective pumping of dust as part of this campaign. And then finally, we still had a component where we were validating ESA's AOLIS wind LiDAR. So these were the overarching objectives for the campaign. Here's the payload. Kind of like a next generation version of the NAMA campaign. So we had dropsondes, microwave radiometer, Doppler wind LiDAR, water vapor and aerosol measurements, free frequency radar. We had some in situ measurements as well, including the CAPS probe to provide measurements of dust particle size distributions. So in addition to that, we also had 3 times per day radio sun launches from the beach. Not a bad location to be working. So here's an overview of our flights. So we were there in operations for about a month, and you can see the various flights here with different science objectives. From the slide, or 2 slides ago, you can see we had a wide range of science objectives, and I can tell you it was often quite challenging to accommodate all the objectives for each mission in an 8-hour flight. So, but I think we did a pretty good job. And some of these are highlighted in the FAMES paper that's just out. So these are the flights that we observed dust on. We had several flights where dust was a primary focus. And again, we had to balance some of the convective objectives of the mission, as well as the dust, as well as the satellite Cabo. So we had 13 missions, as I mentioned, 90 flight hours. We dropped a ton of sondes, 90 radio sondes, and we flew several developing systems, which would later develop downwind, Tropical Storm Hermine, as well as Hurricanes Ian and Fiona. Here are some sort of big picture observations of how the dust intensive properties of backscatter and extinction contrasted from CPEC-CV in Cabo Verde to AW in the Caribbean. You can see moving from the closer to the source region to the receptor region, we have less dust elevated at higher altitudes, similar with the extinction here. In both cases, as I'll show later, we did capture dust in the marine boundary layer, even coming off the coast of Africa. And so we have some contradictory findings to that Carey-Impudi model that I was showing earlier. Here are the intensive properties, so these don't scale with aerosol loading. Aerosol depolarization, so this is a metric of the aerosol shape, non-sphericity. See that evolves a little bit with transport into the Caribbean. And we have some observational evidence that I'll also show later that suggests that dust in the presence of a humid environment can impact these depolarization measurements. Here's LiDAR ratio shown here, pretty constant with transport, around 40 or so. That's used by the Calypso algorithms, I think, today. We did have a smoke event out here. That's a higher LiDAR ratio. It's extinction to backscatter. But primarily we were sampling dust while we were in the field for CPEC-CV. I want to highlight a few cases that I indicated in red. This is the September 9th case, and we had a moderate dust loading coming off the coast here. We performed 2 in situ, we called them parking garages, where we would spiral down from 10 to 12 kilometers to 500 feet above the ocean. You can see that here. Visibly see dust in the marine boundary layer. And we use this sort of this approach to contrast how the dust particle size distribution evolved with transport downwind from the source region. I mentioned that we found instances where dust and water vapor co-varied in the atmosphere. So here's water vapor identified by the halo LiDAR. Here's the peak in dust. You can see they're very well correlated. And we can see in this region we were looking at particle size distributions. This is down close to the surface, higher in the atmosphere, kind of in the heart of this dust layer. And you can see that the particle size distribution didn't really vary, and it was coming off the coast at low altitudes. Again, it's not really being wafted up to these high altitudes like in the conceptual models. This is coming right off the coast. And we have all sorts of cool pictures from the plane of dust, clouds embedded in dust layers here. Another cool thing that we found was we did back trajectories in this event here. And you might look at that and say, oh, that's probably all from the same source region. That's the same dust plume. But some of these back trajectories indicate that these events really are comprised of numerous source regions. There's source regions all over the continent, and just because it looks like a contiguous layer, in reality, it might be comprised of numerous sources. We did an interesting, this is the first time Angela and I flew on the DC-8 together, so we co-managed this flight. There she is in the cockpit. And so after we did the in situ maneuvers, we went down and flew this convective line here, and we had relatively clean air to the southeast. We had relatively moderate dust loading to the northwest. And we did a few cuts through this, this convective line. Here's some imagery from the cockpit. And this is a case that actually developed into Hurricane Fiona, all the way here and strengthened over subsequent days that you can see here in the Hofmuller diagram. So it's an excellent case study for those interested in modeling dust and convective interactions. This is probably my favorite flight. This was later in the campaign. We were doing very early morning takeoffs, so we did not have the benefit of having visible satellite imagery after we took off. The global models were forecasting a pretty low to moderate dust event, but when the sun came up, we saw this. And so we quickly changed our flight plans and focused on this really strong dust event. Optical depth was a 4, it was attenuating the LiDAR. It was the highest dust loading that the DC8's ever sampled. You can see it here, this is the full time-lapse video of us sampling the event. You can see us going all the way down to the surface briefly and going back up. So this is a African easterly wave here, and then on the subsequent day, oops, sorry, I'll get to that in a second. So this was, again, illustrating how the model forecast looked prior to this flight. And so here's the GEOS forecast 1 day prior, sampled along the track that we would fly the next day. Here's what was observed by the halo LiDAR, and you can see that the model was really significantly lower in the magnitude compared to what we observed. Here's the measured extinction from the halo instrument. Here's what was simulated. And it really underscores the value of having observations available to constrain your model. So actually, halfway through this flight, we had MODIS come through, and you can see just the whole loading pop once we assimilated that observation into the forecasting system. I mentioned we flew it the next day. This is the image that I showed earlier. This is Tropical Storm Hermine. Unfortunately, there was a Dakar airspace strike, which is right along this line here, so we could not fly into this region where we wanted to fly. But still, it makes a great back-to-back case study for looking at dust interactions in developing systems. So this image, I always say, kind of encompassed CPEC science. And we were uploading our dropsondes to GTS, so they were getting into the forecasting system, and these observations acquired during this flight were key to upgrading Hermine from Invest 90 to tropical depression at that time. What's key too was our coordination with our European partners. So as I mentioned, we were validating the AOLIS 1 LiDAR. We did legs under the AOLIS LiDAR on 4 flights. These long legs here, typically about 30 minutes or so. And for 2 of the flights, we did coordination with the Slovenian WT-10 aircraft. So they had in situ measurements of aerosol absorption, particle size distribution. So really useful to kind of tie to the remote sensing from the DC-8 as well as the signal measured by AOLIS above. And additionally, on 2 of the flights, we flew directly over the Mindelo. We had the Mindelo ground site operated by our European partners. So we had 4 levels of observations on 2 of these cases. So we're still working with them to try to answer some science questions on dust transport acquired during CPEC-CV. It's a really nice example for how coordinating with partners can really enhance the science return on some of these field campaign missions. This I find fascinating. We saw this both in CPEC's AW as well as CV, but we would often fly over some islands in the presence of dust, and you could really see some of the subgrid wave activity in the dust distributions observed by HALO. Just stuff that global models would never have a hope of capturing. And lots of wind shear around this island. And so we think these are gravity waves induced by the topography here. So those interested in small scale meteorology and aerosols, these are some nice case studies to work with for that as well. If you're interested in looking at the data set, it's stored in two different locations. It's at the NASA ASDC DAC as well as the GHRC DAC. It's all publicly available. PIs are listed there. If you have questions, certainly reach out to myself or Angela, and we can help clarify as needed. So with that, I'll wrap up. So a lot of these are my takes, I think, but in situ observations from the 1960s and 70s from Barbados and the Prospero group really laid the groundwork for our understanding of Saharan dust transport. And this probably a good reminder for grad students is there's a lot of good work done in the 50s, 60s, 70s. And just because those papers are old doesn't mean they're not good. So reminder to do your research, do your literature review. From my point of view too, the LiDAR observations is the key. I've worked a lot with the airborne LiDARs, Calypso, CATS. They're really fundamental for understanding how these dust events interact with clouds and convection during transport, particularly during the field campaigns. While satellite missions are extremely powerful for mapping dust events, for me, it's really the suborbital efforts that have really helped us understand these dust processes. I hope going through some of these campaigns and case studies has convinced you of that. And then, yeah, I mean, even as recent as 2022, some of our observations from CPEC-CV, refute some of the conceptual models, the conceptual thinking. Maybe you think all of these dust events are always dry, right? That's not always the case. We saw covariability with water vapor. These dust particles come from dry lake beds. They're, have crustal salts associated with them, which can uptake the water in these scenarios, impacting its depolarization ratio, for example. And then finally, so many open science questions that I laid out earlier. I really hope that future suborbital efforts are dedicated, in particular, remote sensing combined with in situ aircraft. One of the big challenges of CPECs in our case was you had the remote sensing and you wanted to do in situ maneuvers, couldn't co-locate them. So it would have been really fantastic to have two aircraft coordinated doing remote sensing and in situ measurements. Ground-based assets, to get that high temporal frequency that's needed. I think all these are really critical going forward if we want to answer a lot of those science questions that I laid out at the beginning. That's all I have. Thank you.
We'll start with questions from students. Ian, go ahead.
This is a pretty naive question about just dust in general. As your concentrations decrease as you go westward to West Pacific, is the primary function of that just dust horizontal diffusion, or is it being taken into the ocean, or is it ice nucleation or some other factor that I'm not considering? Is there a consensus on that?
It's serving as ice nuclei. It's getting down the marine boundary layer where it's deposited in the ocean. So there's lots of processes going on that remove dust as it's transported west. And gravitational settling as well. Just naturally it's going to settle with time.
Any questions?
I have a question about the extreme dust event and how the model underestimates it.
Yeah.
Do you think it's most on the emission side or something to do with the weakness in the model?
So it's really hard to answer that question because we have very few observations of the source region. So either the surface winds in the model were not strong enough over a source region, or they were, and they were not over a preferential source region. It was kind of like, right place, wrong time, or something. Wrong time, right place, I don't know. But you have to have those two scenarios line up to emit these big dust events in the model. And once we get off the coast, we can use satellite observations to help adjust for those, events that we did poorly on in terms of the loading.
So I guess, like you said, these dust has sort of been incorporated now into American weather prediction. So do you think that now, is the struggle with modeling dust, is it in the dynamics of it and where it will go, or is it more, do models still struggle with the production of it in Africa?
I think the big problem is the model can't represent, we don't know some processes that are going on that enable the long-range transport of these large particles, for example. If we did know that, I still don't have great hope that a global model would ever be able to represent that because they're coarser resolution. So yeah, I think we're kind of limited by the resolution of the model, even if we did fully understand that process. So.
Yeah, Giselle.
I was just curious with the cases that were associated with dust that later turned into hurricanes. I believe it was Fiona and Hermine.
Yeah.
Do you know how long it took for each of them to become tropical cyclones? Like, is there any variation in both cases?
Yeah, so Hermine was pretty quick. It was within, I guess, 2 days of the wave coming off the coast. Ian and Fiona were much longer. These were convective lines or sort of pockets of organized convection that potentially actually weakened in some cases and then strengthened as they were transported west. So very different time scales for the development of all three.
Okay, we'll open it up to other questions. Larissa, then John.
I'm curious if you have any hypotheses for the mechanism of the covariability between water vapor and dust.
I think this was, we had a dust event emitted off the coast, and it happened to be in the vicinity of the African easterly wave in this case. So it was potentially some moisture advection into the region of where the dust was. I don't think it was coming off the coast moist in this case.
So you don't think there was like a causal relationship between the two?
No, not in this case.
John, another question then.
Yeah, Ed, really interesting. I'm curious, given that, over North Africa, especially the arid parts of it, which is most of it, you can have a mixed layer up to 500 millibars or even deeper, I guess. That doesn't seem like a sufficient explanation for the reservoir of lofted dust that exists over North Africa. So I'm wondering, but maybe it is. So I naively wonder, is there a characteristic synoptic set of events that kick the dust up in North Africa over the southern Mediterranean, and then the dust gets involved in whatever else is going on at lower latitudes?
There's been a lot of research on the impacts of like haboobs and how they can generate some of these intense events. So I think that's one of the main mechanisms for kicking up a lot of these really intense events. And it's the same thing. You have to go over one of these preferential sources that has tons of dust particles that could be lofted to higher parts of the atmosphere.
Okay. And then they have a radiative sustenance component, don't they? Once you lost it, yeah. Okay.
Yep.
Okay, that's really interesting.
So that radiative impact is now captured in at least the GEOS model that I work with. So that's one of the advances. It's not just a passive tracer anymore. It's allowed to interact radiatively with the model as well.
Yeah. Thanks.
Sure.
John, and then we'll do one online.
Go ahead, Jen.
Yeah.
As we mentioned before, I did experience a Saharan outbreak going from west to east. And then I read subsequently that there's some literature in the Pacific Ocean that indicates that some Saharan dust went all the way into the central Pacific. Do you have any knowledge or comments?
Yeah, I mean, occasionally that can happen, but typically from the observations and analysis we did from the TC4 campaign, climatologically a lot of it is removed in the Caribbean basin, but if it wasn't convectively active as the dust was passing through, there are cases where it does get into the Pacific as well.
I was thinking about into the Pacific from the west.
From like the Arabian
From
Peninsula?
India.
Oh yeah. Yeah, that certainly does happen. I'm not focused on that as much, but yeah, you certainly can see that in satellite imagery.
There was a question online, Keith.
Yeah, Jeff Hawkins asks, Several new high-altitude balloon missions are underway, some that do vertical profiles. Do we have cost-effective sensors that could help answer Saharan earlier questions?
Yes, I was at the AVAP's 50th anniversary meeting earlier this year, and I can't recall the group, but they're developing aerosol particle counters that you can attach to these balloons. So that'd be really useful for getting the vertical profile of, I'm sure there's high error bars associated to these, but I think it would be useful for a more affordable way to try to get at some of these problems.
Other questions for Ed? Ian?
I think at one point you mentioned that flight pans had to change as sun came up and visible showed that dust was forming. I'm curious if are there any methods in which we can observe these plumes at night, or is it a function of that they form in the early morning and they
Yeah, they formed overnight and in the early morning, so there wasn't any signature of that in the models or any of the imagery that we saw prior to that. So this is really was a big surprise to everyone in this case.